Welcome to lecture series on design and analysis of algorithm. In today's lecture series, we problem solving technique under dynamic programming called as Floyd's algorithm. So before we see the working of Floyd's algorithm, let's have a quick recap of the topic that we have seen earlier. We have seen what is dynamic programming. We have analyzed the characteristics and components of dynamic programming. We have discussed about the principle of optimality and how to compute a binomial coefficient. Today we will see all-pair shortest path algorithm. What is all-pair shortest path algorithm and what are the various shortest path algorithm available? And under that shortest path algorithm, we are going to discuss about Floyd's algorithm. So this is, let us empathize this problem. So here you want to travel from one place to another. So if you want to travel from one place to another, obviously you will try to find the shortest path. So there are various shortest path problems available. One is single pair shortest path problem. Other is single source shortest path problem. Next is single destination shortest path problem. And last one is all pair shortest path problem. So here is the problem definition. The all pair shortest path problem is the determination of shortest graph distance between every pair of vertices in the given graph. So the problem can be solved using. So let me reiterate the problem definition. The all-pair shortest path problem is about finding the shortest distance between every pair of vertices in a given graph. So there are many algorithms for solving this problem like Dijkstra's algorithm, Floyd-Warshall algorithm. Of all the algorithms available, today we are going to discuss about Floyd's algorithm. So Floyd's algorithm can be applied to graphs that are only if it is a weighted graph. So, and also the graph has to be a connected graph. So you are given a weighted connected graph. So this all pair shortest path problem is to find the shortest distance from each vertex to all the other vertices in the given graph. So here, the distance matrix is an n by n, n cross n matrix. So element dij in the ith row and jth column of the matrix indicates the length of the shortest path from the vertex I to the vertex j. So this algorithm is applicable for both directed as well as undirected graph. This algorithm computes all the elements of each matrix from its immediate predecessor. Let's Dij is equal to the length of shortest path among all the paths from the ith vertex to the jth vertex, where the intermediate vertex number are not higher than ki. So look at this graph. We are going to apply Floyd's algorithm for this kind of graph. This is the formula for calculating the distance. So the distance is calculated as minimum. For example, if I want to calculate the distance for dij of k minus 1, it is calculated as minimum of dij of k minus 1, comma dik of k minus 1 plus tkj of k minus 1. Here I is the source vertex, j is the destination vertex, and k represents the intermediate vertices. Wij represents the weight, that is the distance, value of the distance. So this is the Floyd's algorithm. As we have seen in the previous slide, the distance formula is used. Since we have three vertices here, source vertex, intermediate vertex, and destination vertex, three for loops are used. So here, the distance from each source to destination vertex is updated in the distance matrix. So here A is chosen as the source matrix. So from that source vertex A to all the other vertices like B, C, and D, the distance is updated. Like every time the distance is updated, the new distance is compared with the one in the previous line, in the previous distance matrix. So of both the values are available, of the value that is already available in the previous matrix and the value that is calculated, the minimum value is chosen. For example, if you see here from B to C, the distance is calculated as 5. However, in the previous distance matrix that is available, the distance from B to is infinity. B to C is infinity. So between infinity and 5, 5 is the minimum value. So the distance is updated as 5. Similarly, for all the other vertices, the distance is updated accordingly. Here also from C to A, the distance calculated is 9. However, in the previous distance matrix, The distance from C to A is infinity. So between infinity and 9, 9 is the minimum value. So it is updated. Likewise, the distance is updated for all the other vertices from A. So the time complexity of Floyd's algorithm is for each vertex, it takes n time. So it is order of n cube. So here are some of the assessment questions for your practice. What is the approach that is being followed in Floyd algorithm is dynamic programming approach, and it is used for finding the all pair shortest path. It is not single source shortest path. Dijkstra's algorithm is used for finding single source shortest path. However, Floyd's is used for finding all pair shortest path. So hope you understood what is Floyd's algorithm, and hope you would have understood the difference between Floyd's algorithm and the Dijkstra's algorithm, which we have discussed in the earlier lecture, and how Floyd's algorithm calculates the distance from single source to all the other vertices. Uh, Thanks for watching. In the next lecture video, we will discuss some other problem solving technique.